Let's look at how exothermic and endothermic reactions can be caused in just a little bit more detail. Here's an energy level diagram for an exothermic reaction, and we've got the equation at the top. This is the combustion of methane, and we've talked about how the chemical energy changes in the reaction and how that's related to whether it's exothermic or endothermic, and we talked about the activation energy being required to set off the reaction. Now, the activation energy is required to start off the reaction because it is the energy required to break the initial bonds in the reaction. And what that tells us is that activation energy must be the breaking of bonds, and therefore the breaking of bonds must always, in our diagram, show a rise in energy. Okay, and if you think about it, that makes sense, because if you have a bond holding two atoms together, and you break it, you're going to need to put some energy in order to break this bond, because the whole reason the bond is there is because the molecule is more stable when it's got the bond formed. So you are making it unstable by breaking the bond, and that requires energy. We're raising the amount of energy when we break the bond. Okay, now if that's true, then when we make bonds, we must see the opposite effect. And if I've broken my molecule up into those two atoms and I make the bond again, then what we'll find is that when we make bonds on our energy level diagrams, we are always going to see a down arrow. When we're forming bonds, we will find that we go down in energy. Okay, it's a more stable configuration. The molecule has formed the bond to make itself chemically more stable, energetically more stable, and so we are going down in chemical energy. Okay, so something to notice about this is that the bond making and the bond formation here, the difference in energy is the same for both processes because they're the same atoms that have joined together. So breaking a bond requires energy. Energy is released when bonds form. It takes the same quantity of energy to break a specific bond as is released when the bond is made. Here's an example. If I break a hydrogen molecule up into H atoms, hydrogen atoms, I need 436 kilojoules per mole of hydrogen, of energy. And if I do the reverse process, if I take hydrogen atoms and let them bond, they will release 436 kilojoules per mole of hydrogen molecules of energy. And so last important thing to note is that different bonds will have different bond energies. So for example, a hydrogen-hydrogen bond is 436 kilojoules per mole to break. Whereas if we look at an iodine-iodine bond, if a bond between two iodine atoms, we find that the bond energy is much, much lower, 151 kilojoules per mole. Now, these numbers are not numbers that you need to remember. You just need to be aware that they can be different for different combinations of atoms. So we can see from our energy profile diagram why it is that something is exothermic or endothermic. Now, if I take all my atoms in this reaction, the CH4 and the two oxygen molecules, and I break them all up into atoms, that's going to take energy. Now I've put that line up here. You see I've got carbon atoms, hydrogen atoms, and oxygen atoms up the top there. And what I want to just emphasize here is that that is not what activation energy is. The activation energy is the minimum energy that we need to break the initial bonds, not to break all of them. Here I'm talking about breaking all the bonds in the methane and the oxygen. So this is not the same as the activation energy. So if I break all of those, I will need a certain amount of energy to do that. And so we're going to go up on the graph. All of the bonds being broken is going to require energy. And then my second step is that, well, those atoms there are going to rebond and they're going to form my carbon dioxide and my water. And in doing so, they're going to form lots and lots of bonds, and therefore they're going to release lots and lots of energy. And all of the bonds made there is going to release an awful lot of energy. You can see that this is an exothermic reaction then, because the amount of energy I need to break those original bonds is smaller than the amount of energy that we get out when the atoms reform the bonds. So let's have a look at an endothermic example here. I've got my ethanoic acid and my sodium hydrogen carbonate. Again, to break up all of those into their atoms, we're going to need to put in an awful lot of energy to break all of those original bonds. And when we reform them into the products, we find that we get all of the bonds that we're making release the energy to drop us down from the top level to the product line. You can see with this endothermic reaction that all of the bonds broken require an awful lot more energy than all of the bonds which we're making. So if a reaction is exothermic, more energy is released due to the formation of the bonds than is required to break the bonds. If a reaction is endothermic, more energy is required to break the bonds in the first place than is released due to the formation of those bonds.